Here we go. So, comments, questions, concerns about any piece of this. Based on conversation I heard at the beginning, well, before class even really started, I feel like there should be questions. Yes, Angelina. Sorry? 2B. We're cool with number 1? Everyone's cool with number 1? Okay, sweet. Let's launch straight into number 2. So, multiplication with sig figs. Which is the part that messed you up? Was it the multiplication with sig figs part, or was it the units part? Okay, so like with all of, all of question 2 and all of question 3, how you deal with units is really quite important. You can multiply units together, though, like you would, multiply or divide units like you would numbers or variables. So if I have in 2a, I've got meters times meters gives me meters squared. You likely did that. You didn't bat an eye. We're cool with that, yeah? We can multiply meters and meters and get meters squared? We're cool. Angelina says yeah. The second one, I've got newtons times seconds. That's just going to give me newtons times seconds as my units. Like I can multiply units together just like I do variables or the values that come in front of the units. What a newton second is an entirely different question. But that's what we're doing with the units here. The newton second, you'll learn next year, if you take physics 12, is actually are the units for impulse, which is a change in momentum. We don't do momentum in grade 11. So like C, the same kind of thing. I've got kilograms times meters per second. That's going to give me a kilogram meter per second. These are units for momentum. Meters squared times centimeters. Well, you have to take the centimeters, you convert it into the meters. And I get that. 0.007 meters cubed. Got my kilogram meters per second and my newton seconds here again. Same thing with the division. 5 meters divided by seconds, that's meters per second. I've got kilograms divided by seconds, that's kilograms per second, which is weird, but units can be. And then this one, I've got meters cubed per kilosecond. No idea what that is. That's not really a thing. I mean, you may have, you might look at some of these and say, well, they're weird, but we have no idea because there's lots we haven't learned yet. I'm telling you right now, the meters cubed per kilosecond is not really a thing. Then these ones down here, because we're adding values, I'm not adding, it's like the units function just like the variables do. When you've got 14x plus 12.2x gives you 26x. So 14 meters plus 12.2 meters, 26 meters, assuming you deal with sig figs properly. Angelina, does that help? Make sense? Okay. I'll slide this up here so you guys can see the answers to 5. Comments, questions, concerns about any of this page? Yes, Cricket. 5D. Which part is your question? The sig figs. Okay. So, I have 4 sig figs here, and I've got 2 sig figs here. And I've got 4 sig figs here, and I've got 2 sig figs here. Rules for multiplication and division take us to the least number of sig figs. So the least number of sig figs in all of this is 2. So we've got to round our final answer to 2 sig figs. I also could have messed up in my final answer. 18.01 times 0.41 divided in brackets by 14.62 times 12. I did not mess up. So it could be, you gotta be careful how you punch this thing into your calculator. If you don't put the brackets around this when you shove it into your calculator, it'll divide by this number and then multiply the whole thing by this number, which is going to give you a different value. Are you using a Sharp calculator? Yeah. Oh, does it actually give you 2 distinct lines? Tell me exactly what you're punching. Is this calculator here? Yeah. Okay, tell me exactly what you're punching in.
So I put in the brackets
times. I'm willing to bet there was a missing bracket, which is going to completely alter everything. Any other comments, questions, concerns on any piece of this? Okay, cool. Hearing none, assuming y'all did it. The last little bit out of this introductory chapter, doing some review on some math, introducing to you a little bit of new stuff. We're going to go back to graphing. We love graphing. I've seen it in your guys's, what's it called? The get to know you thing. Some of you said that the thing you love the most in all the world is graphing. And by love the most in all the world, I mean you despise it with every part of your being. So let's do this thing. There's some graphing rules here that I'm not necessarily going to write anything down for you, but I'm going to make you write things down. I've gone through them. I will go through them here for you. When we're graphing things in physics, we're going to be perhaps a little bit more neurotic than you've been in the past. I don't know how neurotic you've been in the past with your graphing. But we want to label the axes, and we want to include the units. At some point in the past, you guys should have learned about the difference between independent and dependent variables. Do those words mean anything to us? Hands up if independent and dependent variable is something you've talked about in the past. Whether or not you remember, it's an entirely different question, but it's in there somewhere. Okay, cool. How many? Hands up if you remember it enough to be able to explain it. Okay. So the independent variable, does anyone remember the independent variable? What an independent variable is, Manuel?
Independent means that it relies on something else.
If you are a strong, independent woman, do you rely on anybody? Okay. So, well, then what must it be? If you are independent, if the independent variable is what?
You rely on nobody.
You rely on nobody. Relies on nothing. And the dependent variable, if you are dependent, now you are connected to something else. You rely on something else. And specifically, the dependent variable typically relies on what? The independent variable. So your clingy man relies on your strong, independent woman. I don't know. I'm just throwing that out there. So the dependent variable relies on, I'm just going to say the IV, sorry, the independent variable. So as the independent variable changes, your dependent variable is also going to change. The classic independent variable that we tend to deal with in math and physics is what? What's the most common one? Time. Time is just going to happen whether you want it to or not. Time is your strong, independent woman here. And things happen as time progresses. So whatever is happening as time moves on is your dependent variable. Typically, the independent variable gets placed on the x-axis. The dependent variable gets placed on the y-axis. I do want to make a note here. We're going to star these two, and throw the word usually in here. This is usually true. It is not always true. Or it's always true until it isn't. Pick one that makes you the most comfortable. We've got to title our graphs, which is perhaps something you haven't done in math before. I don't know. When you are graphing things in physics, there's always a point. We don't just graph them randomly. We want to graph them with some sort of intent. And so we title them y versus x, whatever y and x are. So maybe it's velocity versus time, or just displacement versus time for whatever. So maybe I have a remote control car that I'm racing down the hallway, and I want to find out how fast that thing's going. And so maybe as I time the thing as it goes down the hallway, time as it passes certain distance measurements. So that would be distance versus time for my remote control car. Because the remote control car is the process I'm exploring. Okay, so we have to have a title of some kind. You have to scale each axis. What does that mean? What does it mean to throw a scale on there? Okay, I will tell you what a scale is. Say it this way. Incremental values to help plot data. The scale on the axis, this is the numbers that are going up the side. And maybe there are, well, the scale that you pick, maybe every line is worth 1 on your graph paper. Every line is worth 5 on your graph paper. Every line is worth 10 on your graph paper. You're going to get lots of blank graph paper, and you're going to have to come up with a scale for it. And the scale needs to help plot data, which means the scale needs to make sense. There are good values and bad values for scaling. Anyone want to take a stab at what a good value is for a scale? Say good values. Yeah. Zaid?
1.
Yeah, going up by 1's often not a bad idea. What else could be decent? Yeah, Angelina?
Going up by 5.
Yeah, 5's are good. Not as good, because if you go up by 5's and you need an in-between, the in-between's 2.5. So maybe it depends on your data, but 5 might be good. Yeah. 2's are good, because halfway between pairs of 2's is 1, and you can estimate a quarter pretty easily, which gets you to the half. So depending on your data, 2's might be good.
4 numbers.
Yeah, that's our 1's. Yeah. What else? Yeah. 10's, we like 10's. Okay. These are typically what you're going to end up with. Powers of these, like powers of 10 could work decently. Or multiples of 10 rather could work decently. Numbers you want to avoid, like the plague. 3's and any multiple of 3. 7, you're insane if you're graphing by 7's. Okay. So typically it'll depend on what you're graphing, the kind of data that you've been given, but you're going to have to put together a decent scale and go from there. Another thing that you need to take into account, and students are really bad at this for whatever reason, I do not know. I'm going to do this in red because it drives me crazy. When you're graphing something, use at least half of the graph paper that you are provided with. Doesn't matter if your data is easy or like simple to graph, the graphs should be huge. I'm not going to give you small graph paper either, so make sure your scales take it so that you're using at least half of the graph. The next one goes with what we talked about before with scaling and values. I don't know why that is. Yeah, sorry. This should have been the next point. Use at least half the graph paper. And then the bottom one, plot the points and draw a line of best fit. This is an interesting one. Hands up if you've ever drawn a line of best fit before. You're curious, where? Typically, sorry, in? Oh, in this class. Which physics? Or you started it and decided not to complete it. Gotcha. Welcome back. What's the line of best fit? That's not a bad description. The only thing that I would add to what you said, good curate, is that it's, so we've got data here, this thing down here, these are measured data, and while the lines themselves don't form a straight line, Do they look like they should? Does this look like this is going to be a linear relationship? Yeah, it looks linear. And so when we've got things, I'll just draw a line in here. That is a line of best fit. When we've got data, especially when you're recording it, you're likely not going to be perfect. You're probably not going to get right on every time, every incremental value, so that your data actually, if you were to connect the dots, would form one long straight line. When you're graphing data that you yourself have gathered, if you know it's supposed to be linear, approximate it with a linear relationship, and we want to best approximate the data. So that line of best fit is the line that we're going to draw here. The line of best fit means you want roughly the same amount of data above as you do below. I'll add that in here, roughly. The same amount of data above as below. And it doesn't actually have to go through any of your data points. It just has to be your best approximation for it. A line of best fit is like, I don't know, any of the things you learn in art. I can't tell you exactly how to do it. I can tell you roughly how to do it, and then you're going to get a feel for it as you practice them. So today, there is no, you might have looked at this and said, oh, there's no questions. Yeah, there's questions. They're coming. There's photocopied over there on the side. So you're going to get some time to practice some of this stuff today. Okay? So that is a line of best fit, and we'll get you going with that. A linear relationship. There is, questions about any of this first, the graphing rules? Okay. There is one. Yeah, no. We'll go here. So linear relationships. Linear relationships typically have what kind of equation? Angelina. You are correct. What's M? M is slope. Slope is equal to what? Or conceptually, slope is equal to what? Yeah. Rise over run. Now, practically, what is slope equal to? Like, if you have to give me an equation for it, how would you calculate it? Manuel, is that kind of a hand? Are you scared to commit?
Yes. Is it y minus x over like y2 minus x2? Or is it kind of like that, right?
Is it that, or is it something like that?
It might be something.
It might be something like that. You're Carrot, you have your hand up? It's also something like that. It's basically the good parts of what you said and the good parts of what Manuel said, and if we forget all the bad parts, we get this. Y2 minus Y1, because you want a rise. A rise is a change in Y values, Manuel. And so you want to be going, you can't change, like Y and X they're not related to each other. They're independent of each other, perhaps. So we've got Y2, and I'm subtracting these things because I want a difference in them. So we've got Y2 minus Y1 over a run, which is a horizontal change, and X2 minus an X1. What's B? Angelina. This is a y-intercept. What does that mean? What is a y-intercept? Yeah, Angelina. Okay, so I'll say where the graph hits the y-axis. And typically in math, when you're graphing these things, you're given a set of data points perhaps, and you're going all over the place with these things. The y-axis or the y-intercept rather is often something you use to read off the graph. But when you've been given data points, they might not give you a y-intercept as a data point. Okay? The thing that I see happen all the time is that when students don't have data that nicely hits the y-axis, they make something up for the y-intercept. And the thing that they make up is almost always the same thing. Anyone want to take a guess what people just make up when they're not sure what the y-axis or what the y-intercept is? 0, yes. Okay? They will take the y-intercept and they'll say, oh, well, I don't have data, so I'm just going to assume it's 0, like it goes through the point 0, 0. And that is very rarely true. You have to decide whether or not that's actually a valid data point. So I'm just going to say in here, don't assume zero, 0 is your y-intercept. It might be. That might be a valid option. But it really might not be. And if it's not, we got to figure out why that is. So just in general here, I'll draw a line on this graph. There it is. I'll draw it a little bit thicker so we can actually see it. In this graph here, that point right there is my y-intercept. And if I wanted to calculate the slope, I would pick 2 points off that graph. I'm going to be picky later as to which 2 points those are. Maybe it's this point here and this point here. And I want a rise and I want a run. So my run is going to go to the right and my rise is going to go up. This is the point x2, comma y2. This is the point x1, comma y1. So then my rise here is going to equal my y2 minus y1, and my run right here is going to equal my x2 minus my x1. Because from this point to this point, and it should be positive because this thing's going up and to the right. I'll zoom that in there a little bit for you. This is x2, comma y2, and x1, comma y1. My rise going up and my run going over to the right. Hoping this is bringing back some memories of time long gone. Okay, so when you're drawing a line of best fit, you're going to end up with something that we've already talked about looks like this. This graph has no title, but if we were to throw a title in here, what would we title this thing? Voltage versus current. I'll put it down here at the bottom. I'll zoom this out so you can see it. Put it down here at the bottom. Title doesn't have to go up top. Voltage versus current, and we don't know what's actually being evaluated here, but so let's call it voltage versus current. There's my title. Now, we can't assume that 0, 0 is a valid data point, but let's look at this thing. I've got voltage and I've got current. If I have no voltage, can I have any current? So for this set of data, would it make sense for 0, 0 to be a valid data point? Yes. For this data, it would. So I'm going to add it in here. And I got a ruler, so I'm going to extend my graph a little, my line of best fit here a little bit. See, my line of best fit doesn't necessarily actually go through that point. It almost goes through that point, but not quite. Don't worry if you didn't bring a ruler today, I've got many. When you're analyzing your data, one of the things we're always going to do is we're going to take the slope. Slope's going to give us a relationship here. To find the slope of a straight line, first we want to choose 2 points that are fairly far apart and use points on the line of best fit. Not data points. Do not use points that are labeled as data. We want to take points from our line of best fit that is specifically not data. So, if this is your graph, what 2 points might be decent points to take? Take a look at the graph I've given you, or if you can read it on the screen, read it on the screen. What 2 points might be decent ones to take? Yeah, James.
0, 0, and 0.5.
Does my line go through 0, 0? Then I can't take it. I do not want to use data points. I have to take points from my line of best fit. So 0, 0 is not an option. Even if you're not sure what the values are, there are points on here that are going to be better to take than others. When you're taking options or lines or points on this line as an option for best fit, where do we typically want to try and get? Points that do what? I want points that have nice values, yeah? We don't want to pick value that we have to guess. So if I'm picking points to find the slope of this line, I want to pick points that actually intersect the grid, yeah? Would that make sense? So if I'm looking for points that intersect the grid, this guy right here might be a decent one. So let's add that up here because none of you were saying anything. Choose 2 points that intersect grid points. Like you actually want them to line up with your scale is basically what we're trying to ensure. So that point that I circled down there, and where might another decent one be? We want them fairly far apart if we can get them far apart. I was actually just looking at that one, Manuel. Yeah. That guy right there. Those are 2 decent points. So we're going to make our triangle. When you're calculating the slope, I actually want to see the work on the graph. So now we have to figure out what are the coordinates of these 2 points. Well, we're going to have to go back down and look at the scales. This point here, well, actually, let's do this. So how is this thing scaled? How is the x-axis, I'll say it this way, be more specific. How is the x-axis scaled in this graph? Is it Monday morning? Is that why we're all quiet? Or do we just not know? Which one? Both? Okay. So basically the answer to my question is if I'm asking how is this thing scaled, I just look. So every 1, 2, 3, 4, 5 lines, I'm going up by 0.1. And then I go up 1, 2, 3, 4, 5 more, and I go up, and I'm up another 0.1. 1, 2, 3, 4, 5, I'm up 0.1. So then to figure out what one of these lines is, I take my first major point, my 0.1 here, and I divide it by how many divisions there are between 0 and 0.1. So what is 0.1 divided by 1, 2, 3, 4, 5? 0.02. So every one of these lines is 0.02. So I'm not going to write them all in so long as you understand that, but I'll do this first set for us here. If that's 0.02, that's going to be 0.004, which means the next one's going to be 0.06. That one's going to be 0.08. 0.08. Well, that's really tiny. I'm sorry, that was gross. That's going to take us to 0.1 here. So then what my question then becomes, what is the x-coordinate of that point here? If I take this thing all the way down to the bottom, I'm at 0.3, and I'm going up 1, 2, 3 divisions. So what is that point right there? 0.36. So I've got my x value. Now what's my y value at this point? Manuel already picked a good one because not only is it on the grid, it's nicely on the scale. The y value there is 0.8. Are we lucky enough for the second one? No, we're not. So how is the y-axis scaled?
0.004.
How'd you do it?
I did the same thing, but just with the new numbers.
Okay, so every 1, 2, 3, 4, 5, I'm up 0.2, which means every line is 0.2 divided by 5. 0.2 divided by 5 is 0.04. That's kind of gross, but we'll work with it. So it's going to be 0.04, 0.08, 0.12, 0.16, 0.2. I'll just put the first 4 in there just to give us an idea how this is going to go. And it's going to repeat from there. So now I can make my dotted line go over here so I can actually get to I'm doing the y one first here, I guess. So it's going to be something, comma, something. And this guy's going to be 0.2, and then I'm going up 1, 2, 3, so that's going to give me what? What's my value there? Sorry? One more time?
3.02.
Almost. It'd be 0.32. I started at 0.2 and I added the 0.12. It's going to give me 0.32. Oh, that was, dang it, that was my y value. 0.32. What's my x value here? .14, cool. So now I've got an x value, a y value, an x value, and a y value. So I'm going to do my slope calculation. It's going to be y2 minus y1, so I can shove it in here. 0.8 minus 0.32 over 0.36 minus 0.14. What's my slope? 0. Is it 0 point? Might not be. Someone who with the calculator, what's the slope? 2.18. Can anyone verify that? Okay. Slope needs units. This graph did not include the units. So what's the units for voltage? Voltage is measured in volts. Cool. So how we write that is, we'd say voltage, we'd have our, what this is, and then our units. It's not included here, so we're going to add it. And current is measured in amperes, or we can just say that as amps. So then my slope is 2.18 what? My y values are measured in? Sorry? It's V over A, yeah. My y value is a change in volts. My x value is a change in amps. So this is going to be 2.18 volts per amp. I want you to think back to grade 9 for a second. What value do we get when we divide voltage by current? We get resistance. Just to help you remember things a little bit here, I'll go up to the top. R equals V over I. If we remember back. If we don't, that's okay. Volts per amp would make sense. But if we know that a volt per amp is actually a measure of resistance, then I could write my slope with what units? 2.18. Manuel, you said it. Say it again. Ohms, which I could write as the word ohms, or I could use the symbol. Oh. Yeah, a horseshoe, but the horseshoe has a name. It's the Greek letter omega. That guy is the measure of resistance. Okay, so now we're going to write out the equation for our line of best fit. Let's zoom this out so it's all on here. So we're going to start with y equals mx plus b, and we're going to fill this thing in. What is y representing? You know. What have we labeled the y-axis as? Voltage. So my voltage is going to equal what? Well, m is my slope. My value for the slope was 2.18. X is current. Which, if we remember back here, if R equals V over I, then V equals R times I, which is great, because that's what we're getting here. Voltage is equal to a value for resistance times the current. But now we've got something else here. We've got a plus B. Does our line of best fit go through the point 0, 0? No. So we have to include whatever our y-intercept is. If you had to pick a value for this y-intercept, what value would you probably pick? 0.02. That seems reasonable. It's halfway between here and between 0 and 0.04 plus 0.02. So that would be the equation for our line of best fit. Yes, sir.
coordinates, then did that equation, then you get a 0.13 as the line of x.
What coordinate did you pick? Did you pick a data point?
Yeah.
You can't pick a data point.
Why not?
The data point's not necessarily on the line.
Mm.
It's the equation of the line of best fit. And you have to pick points that are on the line of best fit. You could pick, how would you get 0.13? That wouldn't anyway. That wouldn't make sense. But. The data gives you the relationship, but the relationship you get might not perfectly line up with the data, and that's okay. What is inherent in every measurement we take? Perhaps some guessing. What else is inherent in the measurements we take? It's a 5-letter word, starts with E. Would make a good Wordle word, actually. It's another word for a mistake, but it's not a mistake. It's 3 R's, thank you. Error, okay? There's error in everything. You're not perfect. The machines you use aren't perfect. So this thing right here represents error or uncertainty. Because we know that V is supposed to equal R times I. Well, now I've got V equals R times I plus a little bit. This plus 0.02 here represents the fact that the data we took, the measurements we took, weren't perfect. We can see that because they don't form a perfectly straight line, but we know they're supposed to be linear because it looks like they're supposed to be linear. So we approximate it with a line of best fit. We find the equation for it and we go for it. This idea of error might make you a little uncomfortable. How many of you are uncomfortable right now with this idea of error and adding things to it? A few of you? Okay, cool. If you're not, either you're way more confident than I was or you don't really understand what it means. I don't know. But if you go on in the physics, the 4 of you, you're going to discover that error is your friend. And sometimes you go out of your way to find larger sources of error. Where could I have possibly screwed this up? Because you want your values to line up within a certain percentage error. And sometimes if you think you're better than you are, your percentage error is very, very small. And then your data doesn't, or then your result doesn't match the universe. So you go out and you find data. Well, here's where I could have been bad here. My reflexes might not be here. And all of a sudden, this value for error gets bigger and bigger and bigger. And then all of a sudden, your data that you calculated is within the universe's measured value. And now you're good because you found sufficient error to explain away why it didn't match perfectly. And that's what this idea here is. You're going to want error when you do labs in physics and chemistry later on in life. Is that a hand? Question? Okay, cool. Comments, questions, concerns on any of this? I mean, I'm willing to, how many of you, this is the first time you've done something like this with a line of best, hands up if this is the first time you worked with a line of best fit. Okay, cool. So you're going to do a few of these things for me here. Are there any comments, questions, concerns about this? We feel okay about this? Yak or Carrot? The B value is always the y-intercept. So it's where your line of best fit crosses the y-axis. It depends how you've drawn your axes. Like this is the y-axis right here. The line of best fit crosses it right there. There is no other option for that. It's wherever this line that you drew intersects this line that you will have labeled. Okay, so I want you to play with this stuff. Here's what we're going to do. I apologize in advance. I put these things through the photocopier and the photocopier wasn't lined up properly, but I'm not re-photocopying all of this. This I'm going to give you is just a booklet of empty graph paper. I photocopied it single-sided so that if you need to do work on, like, you need to do math on the back, you can do math on the back. Generally, though, for labs and stuff that we do, the reason I put my slope calculations right on the graph paper instead of this lovely empty box over here is because this is how you're going to be asked to do it.
You go off to UBC, SFU, UFV, and you're taking the first year physics course, and you're going to do a bunch of labs. They want to see the work directly on this thing. I know that because I was a student at 2 of those universities, and I worked at 1 of them. So, as a lab instructor, I know what they want to see. So, put your slope calculations right on the thing. Everything needs to be included on here. And we're going to follow the instructions that I gave you before for graphing. So, I'm going to pass these out, and then I'm going to give you the problems that you're going to be graphing. 1, 2, 3, 5, graph and pass. 3, oh, hold on. 4, you want more? Go straight back. Nope, go back. Nope, go back. That's that one back. So then we give you 2, now you can go straight back there. Like this, 4, all the way back to James. Sorry? Wednesday or Thursday, depending on how the day tomorrow. Rest of today and tomorrow. James doesn't make that. Has to come back. 1, 2, 3, 4. Okay, there we go. Cool. Is there an extra one out there somewhere? No extras? Okay, cool. Okay, so this sheet I've given you, it has the notes for plotting the line graphs right on it. If you forget anything, there it is. And there's 4 exercises. Oh, shoot. I only gave you 3 pieces of graph paper and there's 4 questions. I missed question number 4. Don't do question number 4. Yeah, don't do 4. 4 is weird. Let's do the first 3. It'll give you the premise for the situation. So number 1 is talking about cars traveling down roads, and it's a data collected for the original speed of the car, how long it takes the driver to react to start braking, and then how long it actually takes that car to come to a stop. And this is what you're graphing. There's actually 2 graphs here in front of you. If you need to have any of the graphing, please do let me know. Yes. A ruler. Yes. You're about to say. If you do not have a ruler of your own, I have a few. Okay, rulers here. Please do return them to me at the end when all is said and done. You can't have it.
I actually went into my life because like I was in the line and it was rebellious, but I was like, no, I have to get this. So I went
8 here, 2 there is 10, 2 at Bakerview. Oh no, Manuel. 8, 9, 10. No, I said 12, right? Yeah, it's 12. Yeah, it's 12.
How do you like it?
How do I love teaching? I love teaching.